Good evening, everyone. In the last discussion hour, we discussed about trajectory planning and we saw how to specify trajectories in joint space and in Cartesian space uh, given boundary conditions of the trajectory. So, we saw how to specify cubic trajectories, and they are one of the most widely used trajectories in case of manipulators. And now the focus shifts onto basically if we have a desired or a reference trajectory, then how to track that trajectory accurately. So the focus shifts on control of manipulators. And in this discussion hour, we will cover linear control of a single link manipulator, which basically will help us with the help of a very simple system. It will reveal many important concepts which will formulate the basis for more advanced control schemes that we will discuss in subsequent discussion hours. Also, in this discussion hour, I will be using the lecture notes heavily because of the equations and the schematics that are there in the slides, which you know in order to reproduce them accurately on the notebook, it takes a lot of time. So I will annotate the slides itself, and will go into the depth of the workings of the control schemes. So let's get started. So our objective is clearly defined, that we have the desired trajectory available from the from the motion planner, and now we want to follow it, right? So for a single axis manipulator for a single axis manipulator let me just figure this out. Okay. Okay. Okay, so let's draw it here only. I'll keep referring back and forth between the lecture slide and the notebook. So we have this single link, right? And this is theta t, and we have the desired trajectory theta dt. Let's say the plot of desired trajectory looks something like this, right? So let's say this is the desired trajectory, and we want to provide inputs to this system such that the link follows the desired trajectory as closely as possible. So the goal is to minimize the error. The goal is to minimize the error between the desired and the actual. And for this purpose, we use feedback, and feedback is received through sensors that measure the actual motion. Right. So the components of the so we have in our control scheme, or so basically the controller itself, then there is the feedback. How are we getting the actual data, the feedback, and what is the reference or the desired reference or the desired. So these three components are there. All right. uh, Now let's actually move on to the system at hand. So Here in this example, the link is actuated with respect to using a DC motor, and the DC motor is also having so this is the DC motor, and it has a gear train in front of it. So as we know, gear train helps to uh, multiply the torque output, right, and reduce the speed. So so the output has lower speed than the input, but it has higher torque than the output than the input. So if uh, if let's say 1 newton meter torque is provided by the motor, and we have a gear ratio of 10, then at the output we will get 10 newton meters, right? So that is pretty straightforward. So here we have the first relation, that the rotation of the link is related to the rotation of the motors using the gear ratio, right? So the gear ratio relates the rotation of the link and the rotation of the motor. What we are actually going to control the motor, and in turn the link attached to the motor will be controlled. So we see that if the motor rotates, so here n is equal to, let's say, 1 by 10, or right, or 1 by 8, something like that. So we see that if theta m is multiplied by n, then theta l is of course less than theta m. So let's say if the motor moves by 30 degrees and if the gear ratio is 6, then the link moves by 1/6 of the motor's rotation, so it will move by 30 by 6 degrees, that is 5 degrees, right? So these are the relations between the motor quantities and the link quantities. And so for gear 1 we have, so this is the, if this is the inertia, this is inertia times the angular acceleration, that is the torque, right? Then this is the viscous friction. So viscous friction depends on the angular velocity, right? So it depends on how fast the motor shaft is moving, and the faster it moves, the more the viscous friction experienced is. And tau 1 is the torque acting on gear 1 from gear 2, right? So that is the reaction torque that is being applied due to the meshing between the gear 1 and gear 2, and that is totally equal, summed is equal to the motor torque, right? So tau m is the torque output of the motor, and that is balanced by these quantities. Now the second part of the equation of motion is the link and the gear 2, because link and gear 2 are attached together, right? So they move like one. So basically you can imagine that uh, so if you so this is the motor, right? This is the shaft, then this is the first gear, sorry, and this is the second gear, right? And this is the link. And so if you want to separate the system out, so this will be our one part of the equation of motion, and this is the other, because this gear is rigidly attached to this shaft. There is no relative rotation between the motor shaft and this gear, and there is no relative rotation between the link output shaft and this gear. So these are the output shaft and the gear 2 are treated together, and the motor shaft and the gear 1, they are treated together, right? So the for the link it should be JL, where JL is the inertia of, it's important to note that it's inertia of both the link and the gear, and similarly this is the friction term. And T2 is the torque transmitted to gear 2 by gear 1, and TL is any external disturbance that is acting on the link. Let's say if we are holding the link and pushing the link to one side or the other side, so those moments will come in TL. So now if we assume that there is no energy loss in gear tooth contact, which is not, again, an ideal assumption. So it's an ideal uh, assumption. It's an ideal assumption that this relation holds. So the basically tau omega is the power. So this is power. So what we are saying is that the power transmission is 100%. There is no loss. So we can we can basically write this equation of motion for the entire system, right? So this and this can together be written like that. So let me just write down and show you how that comes. So first equation is Jm times theta m double dot plus Fm theta m dot plus T1 is equal to Tm. That is, this is motor plus gear 1, right? And then we have yeah, so let me start once again. Control of a single link manipulator. So the equation of motion of uh, the the gear 1, and second part is the equation of motion of the link and the gear 2. So let's first write the first equation of motion, that is Jm theta m double dot, right, plus Fm theta m dot plus T1, that is the torque acting on gear 1 due to gear 2, and this all is equal to motor's output torque. This is equation 1. Then we have equation 2, which is JL, that is the inertia of both the load and the link, and both the that's the total load, that is including gear 2 and the link. Then we have the viscous friction, and then we have T2, and that is equal to, yeah, so since this will be, so this is acting on, so this will be minus T2 and this will be equal to TL. So this can come this side, T2 can be taken this side, right? So this is the, and this will be the external disturbance, right? And these are the equations of motion, right? So T2 denotes the torque transmitted to gear 2 by gear 1. Now what we assume is that we are assuming an ideal gear train. We are assuming an ideal gear train where no power loss is there. No power loss. So we have T1 theta m is equal to T2 theta L, right? T1 theta m is T2 theta L. And we also have these relationships between theta L and theta M. So theta L is n times theta M, and similarly the derivatives are also related in the same manner. Right, so we'll use these relations to write the combined equation of motion. So we'll use these two relations to write the combined equation of motion. So let's first write that. So we want to write everything in terms of theta m, because theta m is the variable that we will be actively controlling, right? So the second equation can be rewritten like JL, and then here n theta m double dot plus FL n theta dot m is equal to TL plus T2. Now T2 can be written as T1 theta m by theta L, right? And this can be written as TL plus T1 times theta m by theta L, and theta m by theta L is 1 by n. So this is T1 by n, right? And T1 we have to be, yeah, so we will use this expression to put the value of T1. So finally we will write, so T1 and T2 are the internal torques. Finally we'll write everything in terms of Tm, the motor's output torque, and TL, the external disturbance. So T2 we changed like this, that is T1 theta m by theta L. Theta m by theta L is 1 by n. Now we'll write n times JL theta double dot m plus n times FL theta m dot is equal to TL is equal to TL plus, now T1's value can be put from this equation, so it would be Jm theta m double dot and it will be minus, then minus Fm theta m dot, then plus Tm, and this entire thing will be multiplied by n, sorry, divided by n. Now we take n, multiply n throughout this equation, so this becomes n square, this becomes n times TL, and this n goes away. Right, and we take these theta double dot m terms and theta dot m terms together on the left hand side, so this comes out to be Jm plus n square JL theta m double dot plus Fm plus n square FL theta m dot is equal to Tm plus n times TL, right? So this is the equation that you see in the lecture slides, and this represents the equation of motion of a single link manipulator powered by a geared DC motor. So equation of motion of a single link manipulator powered by a geared DC motor. Geared DC motor. Right. So what we see here is that since, so as we discussed, n is basically, so for a gear ratio of, so n is the speed reduction, so n is the speed reduction, it will be like, let's say, 1 by 10, right, for a gear ratio. So the torque will be multiplied the motor torque is multiplied 10 times at the output, and in the reverse order, if any torque is applied at the output link, right, then its effect is diminished by a factor of 10. So that's what this ntl represents, that if I, let's say, if at the output link I apply a 10 newton meter torque, then the motor experiences a 1 newton meter torque, right, because of this gear train. And similarly, other effects of the load side are also diminished by the factor of speed reduction. So here in this term you see that the reduction is inversely proportional, it is proportional to n square, right? So if the inertia is let's say the inertia of the load side, that is the link and the gear 2, that is that has to, if that is increased 10 times, and if the gear ratio is speed reduction is 1 by 10, then it will be changing by 10 by 100, right? So it will uh, it will still, so the basically the effect of changing the inertia or application of load on the output link, that is diminished by this gear train, right? So that is one additional insight that we get uh, when we derive the equation of motion. Now, yeah, so here also the same thing is mentioned, that if n is small, the effect of load inertia, the load friction, as seen from the motor, is reduced by a factor of n square, and the effect of TL is also reduced by a factor of n. Now we will move on to how to basically control this system. So now this is uh, so the equation of motion that we derived here is the mechanical aspect of the single link manipulator. Now since motor is an electrical device, uh, this is how the motor's working looks like. So we have the armature is stationary, right, and the rotor is a permanent magnet, right? So it has an, so we model this as a RL, or resistive and inductive circuit, RL circuit. So RA is the armature resistance, and LA is the armature inductance, and we apply a voltage VA, and the current in the coil or the windings of the motor is IA. So the higher the current, the more the torque, right? So once we have these notations cleared, we can move ahead. So this is a very important relation, that the torque generated by the motor is directly proportional to the current, as I mentioned, and it is related with this constant called as the torque constant. And the other aspect is the back EMF. So as the so back EMF is basically produced by the motor's own rotor. So since that is that uh, rotor is rotating, so a voltage is induced in the opposite sense of the applied voltage. So that back EMF is basically, acting against the applied voltage. So we have to take care of that also. So The applied voltage VA is basically sum of all these things, that is uh, LA dot, uh, IR, and this kg theta m dot. So this is the relation between the applied voltage and the current of the motor, the current drawn in the motor, and also the angular velocity of the motor. And we can ignore LA for small DC motors, right? So what is next we can do is that this theta, in this equation we have here Tm, that is torque from the motor, and this Tm can be replaced using this relation Kt times Ia, where Ia can be uh, found out using this equation. So let's do that. So we have that Tm is Kt times Ia, and we have that La Ia dot A plus Ra times Ia plus Kg times theta m dot. This is equal to the applied voltage. Now if we ignore this term, then Ia is applied voltage minus the back EMF that is induced, right? So net voltage by resistance of the armature, that is Ra, that is the current that will be flowing, and hence Tm is Kt times this value. So Kt times Va minus Kg theta m times Ra, right? So this is Tm. Now we can put the value of Tm in this equation. That's what we have done here. So Tm is put here. Alright, and after putting the value of Tm here, uh, again the terms having theta m dot and the constant terms are collected. So finally the equation comes out like this, in this form, that is that is the uh, the inertial term, the friction term, is equal to this constant times this voltage, and Td is the basically uh, the disturbance, the torque disturbance that the output link experiences. If the torque disturbance is 0, we can remove this term as well. Okay, so finally our final EOM, including motor electronics, including, because that is also very important. It's an a motor, a link, which is a link, and gear, these are the mechanical system. Motor is an electrical system. So we are studying about robots, right? Robots are electromechanical systems. So we, in our modeling, we need to include the electronic model as well. So finally we have J omega dot plus F omega is equal to K times VA plus TD, right? TD. This is the equation. Let me write it again here. J times omega dot F times omega is equal to kVA plus TD. Okay, so as I mentioned, this is the mechatronics, so mechanics plus electronics behavior of a single link manipulator, and this is, as we see, this is the first order linear differential equation, because we only have first order derivative of omega, and there are no nonlinear terms present here, right? And as we so back EMF, the more the back EMF, the higher the F value is, and so higher is the damping of the system. and the link will rotate if we apply a voltage or if we apply an external disturbance on the link, right? So those are the driving forces here. If that's clear, then we move on to the actual control part of this, this system. So this is our, so basically this is the, the mathematical model of our system. This is the, so as we have been seeing repeatedly throughout this course, that first step to everything starts with developing a mathematical model, right? And models are never designed to be like 100% accurate. We make them accurate enough for our application at hand, right? So here also we took many assumptions, such as, the power loss is, there is no power loss, gear train is ideal, that is a big assumption. Then we ignored the inductance of the motor. So assumptions like these are taken to develop a model which can be handled, the maths can be handled easily. Now what we do, so this equation is in time domain. Time is the independent variable here. This variable is omega t and we have its derivatives, right? So using the Laplace transform, I will not spend time on what is Laplace transform and all. You can read more about it from any mathematics textbook. But taking the Laplace transformation of this becomes Sj omega s plus f omega s is equal to the Laplace transform of these functions. So k times vas plus td times s. Td as a function of s, va as a function of s, omega as a function of s, and omega dot's Laplace transform is s times omega. So s omega s, right? Now we come on to a very important concept known as the transfer function, right? So this is one of the most important concepts in the whole control literature, the transfer function. And it is, the meaning is very easy to understand. It's the ratio of output to input, right? It's simply ratio of output to input, right? So if you know what is your output, if you know what is your input, then you can collect the terms in an equation and write output by input is equal to certain fraction. That becomes your transfer function, and that is what we'll do here. So we have two inputs, right? We have the applied voltage, we have the applied voltage and the external disturbance. So, and we have two transfer functions. So if td is taken as 0, then omega s is equal to, or omega s by vas is equal to k by f plus sj, and if I take omega s by tds, right, so then I take va as 0, then it becomes 1 by f plus sj, right? 1 by f plus js and k by f plus js or sj. Now the expression that we are writing mathematically, it shows relation between the input, that is the applied voltage, and the output, that is the motor speed, angular velocity of the motor, right? So, and this is the relation or the block which relates the input to the output. So va when multiplied with k by js plus f gives us the omega s. Similarly, tds when multiplied by 1 plus js by f gives us omega s. Now together, if both are acting, then both will be added. So how they are added? So td by k and then va, and then both are multiplied with k plus js by f. So when TD is multiplied, then K and K will be cancelled, and this we are getting in inequivalent this only, and VA is multiplied with this anyways. So this is the so this is called as the open loop transfer function. This is the open loop transfer function, right? And second is the closed loop transfer function. Closed loop transfer function. So you see a key difference between these two scenarios. In the first one, we just provide the inputs, multiplied it with the dynamics equation of motion transfer function that we have got, and we get when we and certain output comes out of it. We do not include any feedback of the actual state, and there is no control module in here. So this is open loop control. This is like if let's say 5, if I give 5 volt, then the motor runs at 10, and let's say the angular velocity and the motor voltage has a linear relationship. Then if I want if I want to rate the motor at 10 radian per second, then I should give 5 volt. For 20 radian per second, I should give 10 volt, like this, right? So if let's say I give 10 volts and the motor reaches only 18 radians per second, then there is no mechanism of knowing that, and then taking some corrective actions in the applied voltage such that we reach up to 20 radians per second, which was desired in the first place. So that is the limitation of open loop control, and that's why all the control schemes that are implemented have this feedback part in them, right? So this feedback part is the line that you see coming here, where a sensor is reading the actual angular velocity of the motor and feeding it back to the the desired. So we are here what we are computing. So here what we are doing is basically computing the error, right? Computing the error. Then that error is being fed into the controller. The controller then provides the what is the VA, that we should apply, what is the applied voltage that should be commanded to the motor. And then external disturbances we are not controlling actively, they will come when they will come, and the sum of both is then goes to the plant, or the motor that we have, and finally we get the output rotation, and then we again take the actual output, again feedback to the desired, and like this cycle goes on. So this is the closed loop controller, right? So what is called, this is a closed loop controller. So that's what it is mentioned here, that we have the open loop transfer function and the closed loop transfer function. And what happens when we get feedback is that we get robustness to internal parameter change and external disturbances. So we assume that the VA is Kp times, so this is the simplest possible controller, that whatever the error between the reference and the actual, we multiply it with some constant Kp, and that is our controller ds, right? So ds is equal to Kp times the error is the applied voltage. So if the error is more, then we apply more voltage. If the error is less, then we apply less voltage, right? So for open loop, we have this, that VA is Kp times the desired, right? And if we choose Kp as 1 by K0, right, where K0 is K by F, then we get this, right? So what now we will show is that what is the benefit. So I argued that closed loop controller. Uh, I tried to give you an idea why feedback is important, but we can also show that mathematically also, if we use feedback, then if there is some change in the system parameter, or there is some disturbance, then the effect of that is much reduced in case of a feedback system with feedback than an open loop system, right? So our open loop transfer function. Yeah, so what I'm saying is that what we will show now is that we'll back our argument that it is better to have a closed loop controller with feedback than an open loop controller, by actually showing that mathematically, that if there is, let's say, any change in the system parameter, or there is an external disturbance that the system faces, then its effect is much less in the case of a closed loop controller than in the case of an open loop controller. So uh, chances of the system getting destabilized are much higher in case of an open loop system than in a closed loop system. Of course, we'll have to tune the gains in the closed loop system as well, but with the right gains, we can achieve very accurate behavior, and also handle these changes in the parameters, so robustness basically. So we have our uh, open loop transfer function, that is omega s is k by f plus js times vas. So this is the open loop one. Now here here what we have is that this value k0, right? So k0 is the, let me just refer back what was k0. Kt by ra, and this we discussed here. Open loop without feedback, va is kp times uh, the desired, right? And then kp is chosen to be 1 by k0, where k0 is k by f. Okay, k0 is k by f, and k is this thing. Okay. Mm-hmm. So basically what we are doing is that we are multiplying. So in open in the simplest of, in the open loop one, we are just multiplying the desired angular velocity with kp, and kp we are choosing as 1 by k0, and k0 is defined as k by f. And so this is the scenario. K by f is this. So when s tends to 0, so s tends to 0 means that in steady state. So this is a common you know thing that you will see in control analysis, that s tends to 0. So when s tends to 0, then in steady state, and we have also assume td is 0, so there is no external disturbance and the system is in steady state, right? So the derivative term is, this corresponds to a derivative term, so that is 0. So then k by f is the constant, right? vas. And if, let's say, we write kf is kp times omega desired s, right? That that is the control scheme, the open loop control scheme, because there is no, so this is an open loop control scheme because there is no feedback. This is an open loop control scheme, there is no feedback. So if we choose k times kp sorry, k by f times kp to be 1, then what we get is that omega s is equal to omega ds, right? So that we are getting mathematically, and that is per exactly what we wanted, that the actual and the reference should match, and here it is coming exactly as equal. So this shows, at this point, it seems that the open loop controller is also doing very well what we intended to achieve, right? And let's see now the closed loop one. So I hope the open loop one is clear. What we did is that we wrote the open loop transfer function, right? Then we analyzed this for steady state and for no external disturbances. So then this is the relation, and this k by f is a constant, and our control scheme is this, that applied voltage is a constant kp times the desired angular velocity, and if we put kp as f by k, then this multiplication will be 1, and we will be guaranteed that the actually matches the desired, at least in this model. Now let's have a look at the closed loop transfer function. Closed loop transfer function. So first you have to find out the transfer function, that what is the transfer function, because that we have not computed yet. So this is the desired, this is plus, this is minus, then this goes to ds, right? Let me just see. Let me just pull it from here. All right. So now, now again if we keep td as 0, so we keep td as 0, then we can just directly add this. So it becomes ds times k by js plus f, that is the top block, this block, right? Then we have the output, then we have the feedback. Feedback is just, there is no modification here, whatever is read here is fed back to the comparator where this error is computed, right? This error is computed, and this is the desired trajectory, and this is the actual, right? So this is the closed loop system. And that so on a side note, so this is a very common type of block diagram. So if there is the typical closed loop system is denoted like this, that there is the model, then there is feedback hs, and this is the what is the negative feedback, because we are taking the error, right? We are subtracting them, so negative feedback. So here the transfer function is, and that you can find out on your own also. This becomes 1g by 1 plus gh, right? This is the transfer function where g and h are these two blocks. Now we will do the same for our case. So this becomes phi s, phi ds. So our g is this entire thing. This entire thing is the g here. So d s and k and js plus f by 1 plus h is 1, so this remains again same, and then js plus f. So this becomes kds by KDS plus JS plus F, right? This is and our control DS that we are writing there, that we are finding out like this. So this is our very simple, most simple control scheme, right? So our simplest closed loop control scheme, simplest closed loop in this case, because we are taking in the feedback. So simplest closed loop control scheme is mm, DS is KP. So uh, the output of after DS, after doing DS, the output will be KP omega D minus omega, right? So KP omega D minus omega, right? So that is the, so this becomes, so DS is KP, and we are taking S tends to 0, so this is gone. So this becomes KKP by KKP plus F, right? So this becomes KKP plus KKP by F, and we can we know that K by F is 0, so we can subtract by F by F by F all the terms. So we can write K by F KP, K by F KP plus 1, and this we can write as K0 KP 1 plus K0 KP, right? So so for S tends to 0, TD is equal to 0, the transfer function becomes that omega S is equal to K0 KP by 1 plus K0 KP times omega ds, right? This is the relation. Now in order to make them as close as possible, right, we want our sole objective is to make omega and omega d as close as possible. So that will happen when this thing is as close as when this thing is as close as 1, right? And this is as close as 1 when this term is basically much greater than 1, so that we can ignore the 1, and then K0 KP gets cancelled out, and this is omega d. So for instance, if let's say K0 KP is 1000, so if K0 KP is much greater than 1, then this entire term is close to 1. So for K0 KP much greater than 1, this omega S is close to omega D, right? Close to omega D. We are not getting exact equality here, not getting exact equality here. So at this point it seems that why not use open loop control, but the entire picture has not been revealed yet, and things will become much more interesting when we add disturbances. So next is that. So at this point closed loop seems worse than the open loop, but now we add some changes in the internal parameter. So this delta K0 is the change, right? Then in the case of open loop in steady state, since Kp is set to 1 by K0, so this delta omega is delta K0 by K0. Okay, this is the fraction by which the output changes, right? Now in closed loop what happens is we have this relation between change in the angular velocity and change in the internal parameter. And if k0 kp is much greater than 1, then we see that the the change in so here the change in the angular velocity is directly proportional to the change in the parameter. But here that change in the parameter is can be greatly reduced by this factor, right? So we see that since in closed loop the effect of change in the internal parameter is reduced a lot, uh, and that's why we say that the closed loop uh, no provides robustness to change in parameters. Now similarly, if td is not equal to 0, there is external disturbances, then also we see that if k0 kc is much greater than 1, then effect of these disturbances is also reduced on this omega, right? And that's what we want, that if there is some obstruction in the output link, then that should not affect much. So so this is the closed loop. As we saw, this is the closed loop with a simple control scheme of kp times the error, right? And this is something that sets up neatly for analysis. So till now what we have established is that uh, a closed loop control scheme provides robustness from change in internal parameters, and also robustness from external disturbances. And this is the case where we are using a very simple closed loop control scheme, that is our applied voltage is kp times the error in the actual velocity and the desired angular velocity. So we have this closed loop transfer function. We have this closed loop transfer function, and now we will analyze this transfer function. So first is a step response. So in a step response, the let's say the desired angular velocity is 0, and then at a certain time it is suddenly commanded an angular velocity, right? Then how fast or how slow does the actual velocity reach very close to the desired velocity? That is the step response. That is called as the step response of the system. And we see that this this quantity this is this evolves or grows in form of this, right? 1 minus exponential of this. So as time grows, this terms get smaller and smaller, and the actual velocity also approaches to 1. So so when kp and j when kp and j are positive, right? When kp and j are positive, uh, this f so this entire term f plus kkp by j, when this is positive, then as time goes to infinity, this approaches the desired value, right? So the system is called as stable. And if we increase kp, then the numerator increases, which means this term increases. And so increasing kp means omega actual will approach the desired much faster, right? So this is the analysis of the first order system. when the So we see that by increasing kp we can make this omega reach here much faster. Now if we also include control of angular rotation, so right now we are just having here omega, right, angular velocity. Now if we integrate and we want to control theta, then we have a second order system, because the denominator here now has s square term, so it becomes js square plus fs, right? So this transfer function is a second order because the denominator polynomial is of degree 2 in s, right? And the closed loop transfer function is like this, and this is one of the most studied systems in the control literature, the second order system. And so this is where I will stop for this week. In next week we'll start our discussion from second order systems, and we will see how the values of these kp and other gain parameters affect the behavior of the system. So thank you for joining. If you have any doubts, we can discuss in the next discussion hour.